start. And the reality is, I'm thinking this test is in 2 weeks. Maybe I've got to see. With your group, it may actually go to the 3rd week, just because of the time constraint. Because we're the song says we're getting near the end. I'll show you. And we don't think of it that way, but it is. If you take a look here, I mean, we have the 5th, the 12th, and the 19th left before that, effectively the break period. So, I mean, this will get done today, and surely by the 5th, everything will be done with muscles for you. It really only gives you a week to study or so by the time I get it to you, person. That's why I think I may actually push yours an extra week forward. We'll see. I'm just I'm just thinking out loud, which is the only time I hear myself think. Moving on. So this chapter is less about kind of muscles in general and more about how they work. So it's not a redo. And I said this before in the recorded one that I sent on for Friday. That would have been messaged to you, but via that YouTube. But the reality is that this is really the physio. This is the intricacy, because this is the nervous system as well as the muscle system all wrapped up in one. And then the next time we do the nervous system, and the terminology is a little bit different, but effectively the one reinforces the other. And that's the other thing about doing the 2 units companionly, even though I'm just going to make it, because the muscle part is so confusing. I think there's so much detail. So effectively, we're dealing with a unique kind of an organ that has nerve, artery, and veins all supplying it a tremendous amount of oxygen, a tremendous amount of nutrients, because it's constantly got to utilize ATP. It means more nutrients to metabolize into that. It constantly uses oxygen, and it's constantly using additional ATP to keep resetting itself with those pump units, with the sodium potassium pumps. There's so much there that goes on, and a lot of the problem relates to that. And all of the ability to, when we see what happens when we talk not today, but the material that really comes into focus is next week is oxygen utilization and energy utilization. Those kinds of things become a little more relevant next week. And then we talk a little bit about smooth muscles, and that completes this chapter. So as I recall, the exam itself is probably less than 50 questions. But I mean, I do it intentionally to give, because it's a hard topic. Why confuse it with more detail on the nervous system? We leave basically the peripheral nervous system a little bit. I mean, the central nervous system and the brain and how nerves work in general, and a little bit about the autonomic nervous system. And that's the material for the final. The way I've been doing it here this way for forever. Just a long, approaching 20 years. So the first thing is about these sheaths. It's not important. This is what happens when you look at a muscle, because if you didn't get a chance to listen, it's like the exterior of the muscle we call, and you'll see this with nerves. We have something called epinurium. It's just using those prefixes rather. The epimysium means outside the muscle. It's the connective tissue. It's quite dense and thick. It really gives the muscle a lot of its shape. It's there, and it holds it together. This is not stuff that you could easily cut. Okay, you got to pull and tear. It's the kind of thing in cooking we call it silver skin. It's the stuff you got to remove. Usually you try to broil it, bake it, barbecue, whatever, inedible. But when you pull it out, when you look at it this way, and this is the way meats are cut, they take the long, like imagine if this is a hamstring, but imagine if it was a tenderloin, like a filet mignon, and you slice it this way. Okay, and you look at this picture, the connective tissue it has much more fat content, it's softer. And so this outer wrap here so it's divided these little bundles called fascicles. Surrounding the fascicles is this sort of softer material called perimysium. And when you look inside one of these fascicles, you pull this out, it's an individual muscle fiber. That's the cell. The name fiber in muscle means cell. We're not talking about independently collagen fiber. This fiber has a unique meaning. And really what it is we study that. And moreover, we study the interior because it's just a series of repeat units. and you see this a lot. It was like the osteon in bone, a series of identical repeat units. Basically, we see this in muscle. We see similar nerves, maybe not quite as much. We sort of see more bundles of nerves. Okay, and the cell could be a foot long. And what's unique about it and why we can't replace the ones we're born with, it's got multiple nuclei, and its organelles are really mostly these very interesting bundles of proteins. And the name we give to each of these, so here's the individual cell, and it's just filled with more tubes of protein. These are flexible tubes of protein, and they're unique in the sense that they can contain a very specific arrangement. Sort of interspersed with it, you're going to see there's a lot of mitochondria because you have energy. There's a chemical called glycogen. It's got to have an energy supply. Glycogen is the only way we store carbohydrates. Two places, the liver and skeletal muscles. And basically, we use them as soon as we finish using your muscle, whether you went outside to go to the bathroom, take a phone call, you ran over to the cafe to grab a coffee and came back here, it immediately gets replaced. It's like we always keep our emergencies, and that's what skeletal muscles basically run on. Unless you go into aerobics, and we talk about that, not today, but by the end of the chapter. And then, those are the basic organelles, and then most importantly, the color comes from something called myoglobin. It's similar to hemoglobin, which gives the blood its red color. Myoglobin has iron. You learn about that, the hemoglobin, extensively in the blood unit in AP2. But these iron pigments effectively impart a reddish color, and it works a little bit differently. But and really, that's the difference if you're like me, a foodie, and who wouldn't be? If you're like me, it's the difference. If it's like at Thanksgiving, do you want light meat or dark meat? I mean, they're all built like this, except it's how much myoglobin. So breast meat, and particularly the way that they raise poultry, they've actually changed them, bred them genetically to have big breast meat because people like white meat better. But dark meat has more myoglobin and more fat in it, and it's a lot harder to overcook. And it's also, if you listen to the chefs, that's what they want to use for a lot of their dishes. I'm still a white meat fan. It's okay. So much turkey, so little time. So this is what we're going to look at, the interior. And it's surrounded by another delicate layer called endomysium. That's the individual fibers. I'm not doing origins and insertions. To me, that's lab. I think that's how you learn how muscles work that are there. And really what we're going to look at is not the outer part of the muscle or the fascicle surrounded by perimysium. We're going to look at that fiber. We're going to literally pull out that fiber and look at the protein rods that are in there. Now the terminology is confusing. They're called fibrils. And we're not done yet with being confusing. When we look inside the individual fibril, they have very unique proteins. We're now on an electron microscopic basis, and they are called filaments. So you got fibers, the whole cell, fibrils, the individual flexible rods in the cell, and lastly, filaments. It's a terminology nightmare, particularly for students who have not had this or not had it in university level detail. And I mean, the detail I go into with my advanced phys class next term is similar, but more extensive vis-a-vis nomenclature, how you name it. So, and then we have more. We're not done yet. So that, you take a look here, the individual fiber, okay, it's got the endomysium, but what's this sarco stuff? Sarcolemma. Sarco is the prefix we use for that, for what goes on inside the fiber. Now we're looking at the microscopic muscle. So the sarcolemma is its cell membrane. We understand that there's a liner around the membrane called the endomysium, but now you got a cell membrane called sarcolemma. And we're not done yet. We have a unique kind of endoplasmic reticulum, which is effectively all smooth. Remember, this cell, no, we can't replace it. It's gone out of the cell cycle. It's one of those interesting things that means, what we have, we're born with, and if they're damaged, and we can't make more of them. So at that point, it basically has a very unique thing called the sarcoplasmic reticulum. which is a special kind of smooth endoplasmic reticulum that basically has storage wells. And an old term that they used to use, a biblical term for wells, is called a cistern. They went down to the cistern to gather the water, that type of stuff. My wife is the biblical scholar. I take Bible for 300, Alex, but no, not me. Jeopardy, that game show. Thank you. Brief anecdote, because I mentioned it, and you're here. Maybe you appreciate it. If you did not know, Jeopardy came out in the middling to late 1960s in New York City. The same guy who invented Wheel of Fortune, which is basically the hangman game, invented Jeopardy, named Merv Griffin, since deceased. Extraordinarily wealthy, very talented guy. From a guy who was a singer in a band back in the 40s. So he came up with this idea, and the show, it was free digital. You had little cards that were in. Maybe you've got one of the games. They put little cards, you had to pull them out. And it was 10, 20, 30, 40, 50. And then you double Jeopardy was 20. You get the idea. It wasn't for big money. It was in New York City. My uncle and I both were like the kind of guys. He was much better than I was because he was older. Never missed a question. I mean, he could answer every single question. And I was really good. But I mean, he had the age of his. He graduated #1 in his class at Stevens Institute of Technology, which is still there across from New York City in Hoboken, New Jersey. One of the best engineering schools in the country, right after he got out of the Army in World War II. He went down and auditioned because he loved the show so much. Okay. I didn't miss a question. They didn't take me. I said, what? They said they gave him the reason. Oh, we don't want people who were, in New York metropolitan area. We were from northern New Jersey. We were a 40-minute bus ride away at best. 40 minutes by car, 40 minutes by bus. So, we want to get people involved. They never did. They knew he'd be like the guy who's hosting now. He'd never have missed a question. Never. I mean, he'd been the champion still if it was so long. Crazy. And my mom would still watch that, even well into her 80s, and she'd get the Final Jeopardy before I did. They chose something. And she solved every Wheel of Fortune puzzle before I did. Brother and sister. Side effect. Girls born then did not go to college. Okay. That's money. The only people who went to college are teachers and nurses, period. She was born in 1918. But moving on. So we're going to focus on the sarcolemma. The cytoplasm is called sarcoplasm. Here are the glycosomes with the glycogen. Myoglobin for the oxygen. It's different than hemoglobin, not the same molecule. The little fibrils, modified organelle is a good way to say it, because it's not like we're looking at, here's a peroxisome, and here's a lysosome, and all that stuff. The sarcoplasmic reticulum, and this bad boy called a T-tubule. And you're going to see the animations. The T-tubule basically is an infolding of the sarcolemma that conveys this. It's all about getting the signal from the outside on the surface deep inside, because the outside of this fiber, inside you have all those fibrils, and then deep inside to finally get to the filaments. The T-tubule is known for transverse. They're right angles, and you will see that. The fibrils, rods, thousands, the mass, and because of the way they're arranged, it's where the striped pattern comes from, because skeletal muscles are striated or striped, so are cardiac muscles, except we have voluntary control. And we'll look at the filaments, and even we're going to look at the molecular composition, the way the muscle works. We have what's called a motor protein that changes shape, and in a way it induces this magical process of shortening that occurs. People mistakenly think muscles fold or bend when they contract. They shorten. Proteins are proteins. They slide over And that's what we're going to look at today, what's called the sliding filament theory, how this all comes out. So here's the individual cell, the fiber. Here we are pulling it out, and you're going to see here's the fiber rather. Here's the little rods, the fibril. It's easy for me to make the mistake too. And then look in there. Those little blue to blue guys are called a sarcomere. Just like the osteon is the repeat unit in bone, or the nephron in the kidney, the sarcomere, and again, there could be hundreds or thousands of these all lined up in a row. They are the functional unit in skeletal muscle. Effectively, we study the inside, and we're going to study what makes this banding pattern. And you can just start to see it now. You have areas where they're alternating dark and light. Okay? And those create the stripes. So they're formed from these, and you're going to see the way they overlap a bit. But this is the easy with, and I don't care about the H zone or the M line. Okay? You have the dark regions where these filaments, these unique proteins overlap. Light can't get through it efficiently, so they appear dark. As opposed where they don't overlap, light gets through it pretty easily, so they appear light. How do I remember which is which? Because that's a big problem in anatomy and physiology. Thank you. A whole lot of names to remember. Dark, there's an A. Light, there's an I. There's no A in light, and there's no I in dark. Got it? Light, I, A, dark. Can't miss it ever again. Please. It's like there's no I in team. I always hated that. My son was a goalie. There's an I in goalie. That's an individual position as opposed to a team position. He was good, but never made it past JV. It's all right. I spent the vast amount of my child's growing up years in an ice rink. 7 days. Never mind. Sarcomere. That's what we study. And you're going to see, I'll show you the A band and half an I band. The little blue lines you saw before are called Z discs because they named it because the proteins appear to zigzag. So they call them Z discs. And so, and I guess the analogy is like a series of boxcars, like you'd see a train. You drive along 65, going into town or back out, like, anywhere, going up toward, where is that? Oh, on the tip of my tongue. Rochester and Beaver and all that type of stuff, up 65 north. So moving along, you're going to see that. And so these individual boxcars, those Z discs are effectively they share a Z disc. It's a boundary of each one. And you're going to see they get pulled closer together. So this is a good schematic. And here you can see the overlap. The red, you will come to see, these are the filaments. This is called myosin. Myosin is thick. The blue are actin. Actin is thin. And these are unlike different things that we saw inside the cell that can assemble and deassemble, like microfilaments in the cell, even though the actin's made of a similar molecule. They, microtubules or microfilaments in a cell, these are there for good. Okay? They're a fixed protein structure. If they're damaged, they don't dissolve per se. They just become scar tissue. Here are the Z discs, and they always draw them zigzag like this. And so the actin, this blue, as you're going to see, basically is sort of in the middle. So there's about half of one of these I bands or light bands on either side because there's no overlap. In the middle, not shared from sarcomere to sarcomere, are these thick filaments, the myosin, and where they overlap, that pushes the dark area, except in that H zone or middle area. And you're going to see the way it looks here. This is like standing at a side. It's like I took it, and it was like I had a whole bunch of pencils again. I kind of was looking at the eraser. And you're going to see the way that they share. You'll see that I'm going to go over that illustration and go back. The I band, no overlap, even in the middle. So you have thin filaments, actin. Here you have thick filaments, but where they don't overlap, light can get through. That midline area, that's just an anchor. Light can get through, a lot of space. Here, there's about a 2-to-1 relationship of thin to thick. When we get to smooth muscle, you're going to see it's like 12 or 13-to-1. It still has filaments. We call it smooth because we can't see them easily. I mean, they're electron microscopic. They're there. The striations are there. They're just not visible, even with typical microscopy. Certainly not what they had in the day. It's different with the technology we have today. And this is why this is the overlap. It's like this hexagonal arrangements that you see here. Very interesting. And this is what it looks like. So here you have the individual sarcomere zigzagging. You see this, the actin, it's like I call it like a double string of pearls. The myosin, and this is many of them together. And effectively, when the whole thing works, these guys are going to get pulled closer to the midline. And in doing so, they're going to bring the boundaries together. So imagine, you couldn't imagine it looking at one of those trains along 65, and I'm sure I'll pass it on my way home tonight because I go that way to get to 79. What do? They just keep imagine you're getting closer. It's like you're shrinking lengthwise. Now, boxcars aren't going to do that, but the flexibility of these cells can do that. Just like that. It's very Halloween. It's sort of like one of those, you get into one of those sci-fi movies where they trip something and the room starts to shrink on them. Like the reverse of that stretch room at Disney World, the haunted mansion. Haunted mansion. Love that. My kids love that. He just kept taking me on Space Mountain, knowing I was going to throw up. Moral of the story: don't have children. My wife and I only made that mistake between the two of us 8 different times. 5 for her, 3 for me. And this, see, it kind of looks like a spring. That's called tighten. And that's the elasticity and the extensibility. Muscle, once we go this way, it'll come right back. We can't overstretch it. We could mechanically, but general usage, it's easy to go back to its original shape. And that's the spring-loaded nature, if you want to think of it that way. So I went ahead and I wanted to go back. So it's very orderly arrangement. The actin are thin. The myosin are thick. Okay, and the sarcomere, and you saw that hexagonal arrangement. So the thick filaments, myosin's kind of interesting. I'll show it to you. And what causes the whole game to occur is something called cross-bridging. The myosin heads, and this is part of what we're doing at the end of the day, are already loaded with energy. For you to relax a muscle, for me to fire this muscle, and for me now to relax it, I have to put energy in. Part of what that energy does is it basically recocks this myosin head, changes it. You can see the animations that demonstrate this. When a muscle fires, these are molecularly close. They're angstroms, not millimeters, not micrometers, nanometers apart, tiny, tiny units. And so when the two areas are exposed to one another, I'm using that term advisedly, they bond immediately and it fires. This head pivots or ratchets. It's like a trigger fire. Boom. And it pulls toward the midline. We call it cross bridging. And you will see that. And you'll note the offset as well. That means they're not all in alignment because when they release, think of you climbing. If you were good at an athletic and they did a rope climb. Even if you did a climb and didn't use your feet on a ladder, you couldn't let both hands go. You're going to fall down. So you always have one attached, and they have these offset so that one set can stay attached, one cannot. So it's a very interesting arrangement in that regard. So I will go back and I'm going to go show you start to show you the animation. I do want to talk about the molecular composition and all this that goes on, and we'll get there. But I think it's easier if I show it to you rather than blab excessively. That's all that stuff. I mean, I'm going to go over that. That's why it's complicated. And I feel better if I explain it to you and you listen. Because you can see what's going on here. There's a ton of stuff. Thank you. Thank you. Thank you. Thank you. quit echo. I missed something. Must be losing my touch. See? Let's see. Should have some sound.
Action potentials travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber.
I picked the wrong one. I'm sorry. I wanted to show you how it came together, and I'll show it to you again. Apologies for that. That's why I was scrolling through all that. There's a ton of detail. So what they're talking about is this. It's called excitation, contraction, coupling. I will show you this so you can see. This will show you those T or transverse tubules. They're going to show you the sarcoplasmic
Typically,
reticulum.
a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with a calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm.
This is what I mean.
This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
And so I will back out of it now. Make life easy here for a second. Just to get an answer, because I'm talking about stuff and trying to explain it. It's not so easy. Then I'll show you this one and end with the last one. Because there's so many different events that are here. And I do have a lot of these written down sequentially. And I'm almost sure I have it and typed. But I'll send you a couple of illustrations I took pictures of when I put this stuff on the board. So effectively, that's kind of where we're going with this. I mean, that's why that's why I was reluctant just to say, okay, we're just going to do this. Because I'm going through a lot of stuff. So first things first. We were here. So the actin, on each actin, there's an active site. It's confusing because we named it. It's just like in anatomy, we often name structures not for what they're on, but what they attach to. So you get confused. They're called myosin binding sites on actin, and they're actin binding sites on myosin. I avoid trying to put those in my questions, but I'm not the only one who might pose this question to you, depending on where you're going, career-wise. That's why I mentioned it to you. So these little globules dissolve normally, but when they're all chained together, it becomes a fiber. Hence, you're going to see this is called fibrous actin. I'm just going to say actin. And you can see this, again, it'll look like a string of pearls that are twisted together. what keeps these active sites from touching, and making all that happen that you just saw there. Okay, and when we have an animation that actually shows what happens with regard to that, are what are called regulatory proteins. Proteins are all about shape. These change shape. Okay, they don't change shape all the time. They change shape very specifically for things to happen. There's one. If this is that the active sites are on my phone, along the edges of the case, it's wrapped around them. That's called tropomyosin. And we anchor them in place like thumbtacks, glue, sticky tape, whatever. Those are called troponin. The calcium enters. And when the calcium enters, basically it alters the troponin. The little plugs don't act the same. I'm trying to give you a visual idea, and that's what the animations do. But the reality is it causes these to shift. And when they shift, they expose. They don't fall off, but they change shape and they expose the active sites. They're so close to each other, bang! Immediately they fire. And remember, it's been preloaded because to relax it, you got to load it again. A lot of energy goes into it. We're going to look at energetics, not today. You got to have energy to tell the nerve to tell the muscle to fire. You got to have energy to release the muscle when it fires, and you have the energy to pump active transport to pump the calcium back into those storage wells in the sarcoplasmic reticulum called terminal cisternae. So this is what it looks like. So this is twisted. This is a heavy chain. Doesn't matter to us. Here are the heads, actin binding sites. Those are loaded, ready to go. And you can see how they're trying to demonstrate how they're offset, and you'll see a really good animation. Where on the other hand, the thin filaments, the actin, again, it's like pearls, not white. You can see here are the sites, and notice how in that sort of orangish thread of tropomyosin, it covers them, and the troponin, they've even drawn them like little plugs. They're not like that. It's just proteins have an interesting relationship with one another, and when calcium attaches to it, it changes. Anything that attaches to a protein alters its shape. It doesn't mean dramatically. In this case, it's fairly dramatic. And it flips around and exposes it, and voila, the whole thing goes from there. And the elastic tighten is there. And this is the whole idea of muscular dystrophy. They named the protein that this genetic defect affects after the disease. Dystrophy means irregular growth. DYS means abnormal or improper, inappropriate. Trophy means growth. When something doesn't grow, we call it atrophic, atrophy. So they named, and these other proteins, there's other proteins there too. So this is the most famous. It's called Duchenne's. It's sex-linked recessive, meaning it almost inevitably affects. It's very, very rare to affect women because the X chromosome covers it up. It's passed on the X chromosome, and with men with having a Y and an X, the Y can't cover it up. That's what's meant by sex-linked recessive. And the muscles, they start off healthy and then they begin to deteriorate. Now I think they're living a little longer. This is about 8 years ago. Things are improving in medicine so much that we're able to do this. So here they've named the gene, and the protein for what the name they gave the disease is where it was. These were one of the diseases that people suffered. Nobody had an interest. And years ago, back when AIDS reared its ugly head, they passed legislation to give the big pharmaceutical companies financial incentives to make medications for diseases that weren't that common. And make no mistake, AIDS was not that common. It was made very popular because it affected people in entertainment. Very well-known figures. Rock Hudson was an action figure star who was gay, and he had Liberace. Everybody knew it was a little suspicious, trying to be nice, but he was the hardest ticket to get in Las Vegas. And here are these two very, very popular and really loved entertainers, and the entertainment community with all their money and visibility just said, hey, do something now. If you want us to back you in an election, as politicians. So they passed it, and it's principally for AIDS. And it's a name that you may learn about. I talk about it in a micro called the Orphan Drug Act. It has nothing to do with orphans. It's just disease. It's just funding and incentives for diseases that don't affect a lot of people. But it really is why we have such good stuff in AIDS. That's kind of the backstory with this. And so the baby starts to develop, the muscles then look healthy, but they deteriorate. And finally, and when it gets to respiratory muscles, that's usually what happens. And things have improved, but I mean, if it was 30s, maybe now it's 40s. But you know, for a family, for a parent, those are good things. Okay, and they're just showing how I see that illustration. And so the sarcoplasmic reticulum again is smooth reticulum. We don't need the rough. There's negligible amount of that. Along that long axis of that cylinder, we call a fiber. And you saw in the animation those T tubules, T because they're transverse. And what they do is they abut. That was the triad. You saw that clearly in the animation. You had, it's like this. I mean, these bulbous enlargements in the sarcoplasmic reticulum, it's where the calcium is stored and it's released. And this is where the students have the biggest problem. Because now we're going to start talking about voltage and ligand-gated channels. If you remember that illustration, the shock wave, the impulse went down the nerve through the sarcolemma into the transverse tubule and basically clicked the switch. That electric switch, if you will, opened the door to allow the calcium coming. It's called a calcium voltage-gated channel. And it gets more confusing because there's another one in this process as well. This is what you don't want to hear. The T tubules just have surface area. Okay, the impulse is carried in. They happen to be at the A and I band. That's the triad. You should know what makes up a triad. That's there. That's the so-called triad relationships. And the fact that they have the gateway are called voltage sensors. And because it's calcium, the parlance that we use, the naming convention we use, voltage-gated calcium channels. And you're going to see one at the end of the nerve that tells the muscle to fire anyway. So that's really what you were seeing in that animation. That's what kind of why I put that cart before horse, because I have to show you how the nerve impulse got there. And that's where I had this information already up. But I'll read it to you. I will send my poor artwork for you, but you'll be able to see because it's fairly straightforward. And I think one time I typed it up, so it's sitting somewhere. I'm betting it was around like COVID lockdown time, that area. So I probably have some documents. I'll find that are there. But here's the triads, and they're all over. So I mean, and this is how it gets to the interior. It doesn't go along the outside. So the contraction is the cross bridging, and basically when they talk about tension, the muscle starts to fire. It has to fire enough to lift or move whatever you're moving. Like I can pretty easily lift the bone. I'd have a pretty tough time lifting. I couldn't lift this, but my muscles would try. They'd build up tension, but I couldn't get them to shorten. It's all about the load. That's physics. We don't do physics. This is the sliding filament model. And again, it's about overlapping and these cross bridges. You're going to see that. And effectively, this is what you saw in that animation. Basically, those borders, the sarcomere, come closer together. Okay, and the light bands shorten. It's a visual thing. They're still there, but now you see less of them because effectively the walls are coming in. We're shorting. It's like a telescoping phenomenon. That's there. So this is easier to show it than to talk. Here's a relaxed unit. Exactly. This is the electron micrograph. There's the dark band. There's mid-zone. Kind of looks, people say, like a letter H. You bought it. Here's light on either side. Here's the cursor. Look what happens to the next slide. My cursor moved. Here's the cursor. Look what happened when I relax it. When I contract it. You can see when it's contracted, look what happens. The I band shortens, at least by half. The walls have come in significantly closer to the Z discs. you can see what happens to the A bands. I mean, not the A bands, the actin filaments. They're being closer together. Look where they were before. This is really, as far as this is maximally contracted because these guys can't go any farther. There's a protein in the way that won't let them overlap, but you can't over contract the muscle. I mean, the muscle might go into spasm. There might be waste products. That's different. It's there, and that's what they're trying. Here's the elastic being stretched, and you see when we backspace it, it'll start to relax, just like any spring. We're coiling it more, and that's the elasticity or extensibility that we talk about. And so this is the whole thing about how we make this magical process work. This is voluntary. I'm going to move this muscle. You're going to change. We do it. You feel I'm uncomfortable here. I'll do this. I'll do this. At least you're not sitting in the lab on the wooden chairs. Look at the bright side. We all do this, whether you're at home, whether you're in a dorm room, wherever you reside. So, but we still are making a conscious decision, even if we didn't say, some things we're doing, some things that are almost sort of routine or automatic, but you are still voluntarily controlling it. So, because these are excitable cells, we send a signal from our brain, typically to the spinal cord. It can be a cranial nerve, but that's a different lecture. And there's a 2-nerve circuit. From the spinal cord, the nerve goes to the muscle. Hey, you, move. I'm thirsty. Grab my drink. I don't feel like it. Grab it anyway. Do what you're told. This is my wife. I don't have an option. Let the dog out. But let the dog out. Yes, dear. Remember that. So the excitable cells carry that impulse. So we're telling the nerve, first nerve from our brain, do this. The nerve from your brain goes, okay, spinal cord, send this out to the arm, do this. It's all about a neurotransmitter. Nerves talk to other nerves by chemicals, with very, very few exceptions. That's actually the rate, that's the slow part, and we're talking about milliseconds. Thousandths of a second, 3 to 5 thousandths of a second to get this message. The chemical is all the same between nerve and muscles. When we get to the next chapter there's a whole lot of different neurotransmitters. We're going to look at about 10 of them. They all have different ways of getting their message across, and different messages depending on what they contact. This one is famous. It's called acetylcholine. It's made from common ingredients. You want to think of it that way. It's like flour and water. I mean, we're making some kind of a dough. Effectively, acetic acid, which is vinegar, we use acetyl groups all over the place. Choline, we use in a lot of other things. Inside that nerve, it basically makes that, bonds them together. And what they do is they're put into little packets called synaptic vesicles. These little packets of synaptic vesicles store them. And when the impulse goes down the nerve, basically it triggers their release, as you will see shortly. It's spit out of the nerve. I used to do this lecture to explain how nerves communicated when I would give trial lectures to get hired. I didn't have to do one here. Okay, but in all the other schools I worked at or applied to for full-time teaching positions, I did this. This is ages ago. My daughter's going to be 40, so this is when she was about 15, maybe 25 years ago. So I'm trying to do this. I was explaining a little bit to her. She goes, you know what that sounds like? Pixie sticks. You know pixie sticks? With the 5 different colors, different neurotransmitters. You snip the top off, and nerve impulse, out comes powder. It was a little messy. It was good. So, thanks again. You never set foot in a college door other than to go to a party. Your kind of girl. My daughter is a trip. She's settled down. If I'm feeling frisky one day, I'll show you what she looked like at her wedding. After. She got out of the wedding dress and got into her. If I said Austin Powers, do you know what movie I'm talking about? Remember, like back from the 60s, Go-Go Girls? She did that number. miniskirt, boots, going techno. That's my girl. So it causes and acetylcholine. This is where it gets confusing. You're going to see that it goes across, and in order to send its message to the nerve, from the nerve to the muscle rather, it has to trigger receptors which receive the chemical acetylcholine. They're called chemical gated or ligand gated. So you're going to see a combination as we look at this animation of different channels. Chemicals open one, voltage opens others, and it can get very confusing. So you're going to see both of these. So, and down the road, we're going to even see more complexity, because in order to spread that all over that nerve fiber, that individual cell, we have to reach something called threshold. Threshold means we have stimulated it enough to reach other kinds of receptors that are voltage gated. And that's where the complexity that I don't spend a lot of time in with you, but I think you should have some familiarity. This is all it means. The term chemical or ligand, interchangeable. Effectively, they're the trigger that opens that gateway. And at the motor end plate, where the nerve effectively contacts the muscle, it doesn't contact it directly. There's a little space, like a joint space, but infinitely small. Effectively, that's where the acetylcholine gets pushed out, a la the pixie sticks, and opens that gateway, and in rushes sodium and out rushes potassium. In that 3-to-2 relationship, that's very significant. 3 sodiums in, 2 potassiums out. What that means, the inside's going to get a little more positive or less negative, and that way the threshold, if resting is -70, threshold's about -55. So if you get enough of these gates opening at the same time, and if they stay open, so the more the signal comes, the more the acetylcholine, the longer it's in there, it will reach this sort of imaginary level called threshold, and that signal will spread rapidly all over in every direction on that muscle fiber. We call that, it's very RMU, it's unstoppable. It's unstoppable. They just had a caption like that in one of the newspapers with one of the politicians, unstoppable. Probably has to pay money to RMU for that. And that unstoppable action potential just rapidly goes through and triggers this response throughout. And so this is one of the things that will trigger. It's called a voltage gated channel. It's not like the one for calcium. It's going to be ones that involve sodium and potassium. This bad boy, we really don't talk about now. It may be mentioned a little bit when we do the nervous system. That's called an inactivation gate. If these are doorways that open, this opens with a chemical, this opens with an electrical signal, this is the lock. So it swings over, and not only does the gate close, it's like a latch. Until that latch moves away, that gate can't be used. That's something that they talk about here that's much more relevant with the heart. It's called an absolute refractory period. There has to be a finite amount of time, albeit tiny, for nerves and muscles. For the heart, it's about a quarter of a second, where it cannot contract again. Prevents the heart from getting a muscle spasm. So when somebody tells you, oh, I had a heart spasm, or grandma had a heart spasm, but she's okay, impossible. Doesn't work that way. She probably had pain from like a blood supply. Maybe there was a heart attack. We don't know. Those are all different parts of the diagnostic criteria. So muscles are stimulated. Somatic means your body. So we're talking about basically muscles and joints. The axons are really long thread-like fibers that zip down. And again, I have to show you. They'll show it to you. And so that's the end of the nerve that transmits. And at the very end of the nerve, it branches hundreds, if not thousands of times, and forms what we call junction points. You're going to see they're called motor units. There's a better illustration than my bad artwork. They kind of sit on top of that muscle fiber and release this chemical. And it's called the motor end plate. So you're going to see all of that. These are a bunch of fibers. bunch of individual cells. So here's your brain, here's the muscle. Here you can see they're almost just sitting on there, little bulbs all along these fibers. And it's not always in the same place. If you use the same piece, it would fatigue. So we use this arrangements to prevent fatigue. So there's a cleft. You're going to hear the term synapse or synapse a lot. It's where nerve and nerve meet, or nerve and muscle, or nerve and end item meet. And that synapse is a space. So it's an impossibly tiny distance between two objects on a microscopic basis. And they're so close, it will flood as soon as that stuff is released. I mean, it floods the area in vast amounts, and it's going to trigger something. The question is how long it stays there, and is it in an isolated area? But the reason it's all over is so that those motor units don't get damaged or fatigued. Has the synaptic vesicles, they contain acetylcholine, and there's a lot of surface area. You're going to see that in a second. They're called junctional folds, and this is in the motor end plate. They're infoldings of the membrane with proteins that act as these receptors. And this is what it looks like. So down comes, and you're going to see the animation in a second. Down comes the signal. This is, you're going to see it. This is a voltage-gated receptor. Calcium from outside around the nerve shoots in, allows these vesicles to bond and spit out their acetylcholine and cause this phenomenon. And so that's what we're talking about now. Events at the neuromuscular junction and the muscle fiber excitation. So this is a summary that you're going to see. The action potential arrives. It opens up channels. And why I made a point of telling you it's outside. In the calcium that we're talking about that allowed the sarcolemma and the sarcomeres to shorten is intracellular calcium. It's different. It's already in the muscle. Okay. You're going to see smooth muscles, heart muscle, and the nerves has to do with extracellular calcium. I'm pointing that out because that's the kind of thing that can fool people on a test. Oh, extracellular calcium levels are, are affected by those voltage-gated channels in the T tubules of the triad. No, they're not. Different kind of channel entirely, different kind of calcium. And you see that a lot. There's a lot of things that are in the cell already and stay in there, and a lot that don't. So the calcium entry here causes the acetylcholine to be released. It spits across that area, it binds, and if there's enough of it, we're going to get an action potential. And then you're going to see how we get rid of it. As soon as we release it, it starts getting rid of it, because you're going to hear about an enzyme that's there all the time. So rather than go through this, now I'll play that other animation and come back and show you this. And it's probably more than we can, probably enough info for today.
Nerve impulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber.
Just like you see this, there's a slide that looks just like this.
The events at the neuromuscular junction occur in 7 coordinated steps. Step 1. An action potential travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7. Once the membrane potential reaches a threshold value, an action potential propagates along the sarcolemma. Neurotransmission to a muscle fiber ceases when acetylcholine is removed from the synaptic cleft. This removal occurs in 2 ways. 1. Acetylcholine diffuses away from the synapse. 2. Acetylcholine is broken down by the enzyme acetylcholinesterase to acetic acid and choline. Choline is then transported into the axon terminal for the resynthesis of acetylcholine.
And that's everything. I'll go over this again just to show you. So effectively, this is it. The first thing, this is that arrangement of the motor end plate, and it's very much how it looks microscopically with an electron micro. It's like little feet, and they're sitting but not touching, but very, very close. It's called a motor end plate. So there's more than one of them. And what happens is first that signal, when that signal comes down, it doesn't just release the acetylcholine, although it's there. That's when those voltage, you can see them below here, the voltage gated calcium channels open. Calcium from outside the cell goes in, causes synaptic vessels to spit out their acetylcholine. That's where Botox works. It stops that process. That's when it works specifically on the neuromuscular junction, skeletal muscle. We use it in other places, but it paralyzes them in such a way that they can't. And that's why if there's wrinkles, which are more spasms, they release. This for about 6 months, but once you start using it, it's cosmetically. I mean, that's back to my daughter. I mean, she worked at a facility, at a business that sold these multi-$1,000 packages to very wealthy ladies as they got older who wanted to retain their looks. So they get a pretty girl who she was a trained esthetician. So I mean, it was sort of her business in a way. So as we go back, here's the calcium. Here, pouring out the acetylcholine goes right across. So these are ligand or chemically gated channels. And effectively what happens, they open it. There's so many of them because of all those folds. The red, sodium goes in, the blue, potassium goes out, more sodium than potassium, 3-2. And what happens is, if it's sufficient, it'll take this impulse. The impulse, if it's just localized in the center of this, wouldn't be enough. But as soon as it goes far enough, it can trigger. You see where that sort of that edge of that bright light is over as you're looking at this on the right. That is where you're going to find more of these channels. There. You're going to see these special channels called, which I'm not going to do today because you got enough of this detail. I'll probably send you that voltage gated sodium then potassium channels. You're going to see it. I don't go crazy about it. That's what I do with my advanced phys, because I can't go into all this detail because it just snows people. Now what happens, how do we get rid of it? There's an enzyme called acetylcholinesterase. They're depicting those guys. You can see the name there. It gobbles up the acetylcholine. It goes away 3 ways, and this is true for all neurotransmitters. They don't all do 3, but acetylcholine is a good example. And that's the best one to know about. It's the one we have the most of. It's in your brain. It's in the autonomic nervous system. It's in every neuromuscular junction. This is the one to know about. So acetylcholinesterase, acetylcholine does 3 things. It diffuses. It's not like a locked room. It can diffuse or spread out. It can be metabolized this way. Metabolized means are broken down or gobbled up. The enzyme breaks it apart to acetic acid, which we use, and the choline is recycled. The appropriate name for this is called reuptake. Reuptake is a majorly important thing to understand going forward. So the choline is sucked back up, reprocessed into more acetylcholine, and reused. The body's very efficient in recycling things. This is a recycling mechanism. When we put somebody on a medicine for bipolar, for ADHD, for OCD, eating disorders, pick one. Almost all of those medications inhibit reuptake and make more of chemicals available, particularly one you're going to learn about called serotonin. They're very specific. That's an important part of the nervous system. That's why it's so important to understand. We make more of it available, and in doing so, a lot of times we can change the receptors in the way that they transmit signals. It's very interesting, very advanced, and to understand, because whatever field you're going to know somebody in your life who's on these meds, knowing the side effects, knowing the pitfalls. There is no medicine that doesn't potentially have problems with it. And so that's what they're showing, those three methods. That was part of this particular animation. And so again, some people have an autoimmune disease, just like we learned about autoimmune diseases like rheumatoid arthritis affecting joints. This affects the receptors. And again, we actually used agents to try to inhibit the acetylcholinesterase. The problem with doing that, that's very easy to do in very small doses. And again, it affects their respiratory muscles. That's what shortens their life. Science, when you understand science and medicine, you can go in two directions. Thankfully, thank the good Lord, most people do it for good. A lot of people, they may want to make money, they do this, they do that. It doesn't matter to me. If they're doing something for good, it's fine. People have exploited this for bad. If you are familiar with chemical weapons, this is principally how they work. They have acetylcholinesterase inhibitors. The acetylcholine is there. They release it in such large amounts, so rapidly active, that your muscles immediately spasm and you can't relax them. Respiratory muscles. So if you see, these were first used in World War I by both sides. These have been used as recently as Saddam Hussein in Iraq back in 1988. Bashar al-Assad, the guy who they kicked out, the Syrians kicked out, who was a family leadership, he's now in Russia hiding on his own people. Used by a terrorist group in the subways in Japan. It's called sarin gas. When you hear about sarin gas, VX gas, they are acetylcholinesterase inhibitors. So I mean, it's the two-edged sword of understanding science and medicine. I mean, you hopefully help people, but you can hurt people. That's good. That's why it's just terrifying. And so that's just giving you an example of that myasthenia gravis. I'm going to back up. This just summarizes the events. It's too hard for me to read. Probably hard for you to read. So we look through it individually. Maybe you can blow it up. And there's a lot of steps. We've done this. Okay, I looked at this area a little bit, the excitation, contraction, coupling. You'll see we'll go over it again. But basically, it just means that signal was strong enough to reach an action potential. And in doing so, it spread throughout the whole fiber. So we got to this, and if it doesn't reach there, they're called end plate potentials. It's like deciding to move. I'm really thirsty, but I am too lazy to go out and go to the kitchen and get something to drink. Which is why on my nightstand, I have something to drink. See, I figured that one out. And when it finally reaches an action potential, what happens is that signal spreads out and contacts these voltage channels that allow unbelievably large sums of sodium in and then unbelievably large sums of potassium out. When the sodium comes in, it flips the polarity. No longer is it positive on the outside, negative on the inside. It's magically positive on the inside. It changes the polarity. That's depolarization. And immediately after that, sodium channels open, and we can find potassium channels open, and out comes potassium to break it, to revert it or repolarize. It happens so rapidly, it looks like that. So this is the end plate just enough for a signal to get going. But depolarization, if the end plate reaches enough to contact these these voltage-gated sodiums in, large influx, action potential, unstoppable, I know, and spreads all over throughout that whole fiber. And just right after that, the potassium channels open, and they offset it electrically. The electrical events happen first. Then the sodium potassium pumps get busy, and they restore it chemically. They pump out the sodium, pump back in the potassium and rapidly so. And they're working all the time. And then after that, you're going to see that electrical events precede chemical events, restoring the balance inside that fiber or cell, and electrical events still precede mechanical events. That's why they call it excitation contraction coupling, not the other way around. Excitation is electrical. And so that's what they're describing to you there. So you see the repolarization, and then this is what I was telling about before. There's in nerve and muscle, there's very, very tiny refractory. Okay. And the sodium potassium pumps restore it. So it's very tiny. And this is what they're trying to show you. Very fast up, a little slower going down. Not a lot. And so, I mean, in a matter of, what's this? Less than 10 milliseconds? Less than 1/100th of a second? Conditions are restored and it can fire again. How fast can you do this until it fatigues for a long time? Nerves even less. Just a very phenomenal process. And that was that animation I showed you. You're going to see when I send you this animation. We're done, by the way. This will go over all these events, and then we're going to look lastly at the cross bridge cycle that you're done. Okay? That'll conclude this particular PowerPoint, and the other stuff will come. It's quicker and easier. So I'm guessing we'll have this completed sometime, not this time you come in, but the next time. Thank you. You're good. Good to go. My voice, we'll get there.